Bien, estamos ao vivo, em vivo.
Okay. Did we start the... Okay. Okay, let's start. Welcome, everybody. This is our last day of conference. This is session 7, room B. And it's about the track of this session is called Projection and Predictions. Today, we will review 4 articles that are around, let's say, this idea of, we can say, design automation, prediction, but basically using artificial intelligence, machine learning for generative design, or making sense of the data to start predicting, right? Because the more data we have, we have the chance to create, to propose predictions, right, based on correlations and projections of based on what we have. Okay, so we will start with 5 articles today. The first article, let me start. I need to open the videos. We will open the video here. Okay, give me a second. And I'm gonna start sharing my screen. And we'll project the videos first, and then we'll have time for questions. Okay, let me start. Okay, give me a second. Share. I will start with the screen 1. Okay, I'm gonna start sharing my screen. Let's see the video. 100. Sorry, it's 44, right? 144. Let's start.
Hello everyone, today I'm gonna present this paper titled as a data-driven participatory decision model proposal in the context of urban vibrancy. This is the outline of the research. The research topic is about the livability, and which is an urban policy and an umbrella term to explain what makes a place successful. And we recognize its multidimensionality and focus on the vibrancy. So we position ourselves in the intersection of data-driven and participatory approach. So we focus from the data-driven perspective evaluation of the vibrancy. And we conduct a knowledge discovery process through the physical and digital urban data layers to understand the urban vibrancy by revealing the relational network between the variables. In this structure of the paper, it starts with literature review, then vibrancy measures and case study and Bayesian inference. And then the methodology, we mentioned about the data collection, quantify and analyzing methods. And in the results, there are both mapping and BBN results. So those are the research questions. To answer these questions, first we conduct a causal knowledge discovery process with BBM, and then we evaluate the causality of the relations through the expert participation. So the results are the activity diversity and attractiveness of the cultural landscape are important for urban vibrancy. Those are the variables that we use to measure the urban vibrancy, mainly taken from these references. So the active people density is the dependent, and the activity spatial temporal diversity indices within the accessibility and cultural landmark properties and its visitation rate are the dependent variables in the study. So Istanbul Historical Peninsula is the test bed. We examine its vibrancy conditions through the crowdsourcing of LBSN data and digitizing the administrative maps. The location-based network data is the data obtained from locative technologies. So in the urban literature, it has been to reveal the attraction points and to reveal the vital centers. We adopt a big data approach together and analyze big amount of geospatial data, and we utilize the Bayesian inferences as a method of big data analysis. The Bayesian Belief Network, BBN, is inspired from human probabilistic reasoning capabilities in uncertain conditions. It's type of artificial intelligence method. And automated BBN construction from data is provided through the learning algorithms. We utilize these learning algorithms. Here, the algorithms learn the probability distribution from the data sets and establish BBN automatically. It's an example of supervised learning. This is the steps of methodology. So we apply different data source for scared check-ins to quantify the user density. Google Places API for information about activity places, and Flickr image metadata for visitation rate. Different measuring methods also to gauge these determinants, which are the entropy-based diversity indices, cumulative-based accessibility opportunities, spatial statistical method, fishnet-based density or visitor density, and with photo user day method determined by Wood and other researchers for visitation rate. So we utilize the BBN as a knowledge discovery tool, as we mentioned, and we evaluate this BBN network in terms of its causality based on the expert participation. Those are the flowcharts of data scraping from different data sources. And here we can see that each vibrancy measure and corresponding measuring method formula and the different data sources. So we utilize the necessary path conditioned learning algorithm to construct a BBN network from this data set. Here, this is the result BBN network. And first, we discretize data from ratio to interval level. Then the MPC algorithm established this BBN network, but there are some uncertainties. To resolve these uncertainties, we benefit from the correlational test results, statistical test result. Based on that, we make selection to eliminate the expert bias, and those are the resultant BBN construction. This is the semi-automated BBN construction. So in the results, we can say that the area has high level of accessibility and high activity diversity as well, and the abundance of cultural landmarks. Visitor density is clustered in cultural and commercial zones mainly. So, but the amount of the public space is insufficient in this area, and the activity places should be balanced and spread equally for balanced mixed use, because here there is an overwhelming majority of the commercial functions. This is the map results, Google Places results, the first one. The second one is the fishnet grid-based Foursquare density results, user density results, was point-based and grid-based results, and those are the Flickr results, the user clustered around the landmarks. So here we map the vibrancy measures results according to the neighborhoods. Cankurtaran is the most vibrant neighborhood, and Sultanahmet and Eminönü are the districts which are saturated with the vibrancy measures. This is the BBN analysis results evaluation. So we evaluate the results based on the conditional probability table. We created this conditional probability table by changing a independent variable condition from for instance, this being low condition, setting to 100%, and then we monitor its effect on the user density. So here we can say that the visitation rate has the strongest effect on user density than the cultural density in parallel. Place rating and activity diversity and the accessibility and public open space has the weakest effect in this area on user density. So this is the survey results. In the survey, we ask participants to assess the correlation and causality of the relational pairs, and we then derive a causal map. In this map, we can see that the 85% of the BBN associations has been found causal by participants, only 15% found correlational. So we expect that this causal map can support urban planners more efficiently. Those are the causal relationships and the correlational relationships found by the experts. This is the results, the rate of the participants' response. So here in the results, we can say that spreading the activities to daytime and places and creating an urban pattern is important for a successful quarters, as Jacobs and Montgomery also emphasized. In the conclusion, we can say that it's useful for user planners since it's consider the visitor and activity related parameters, so it's an inclusive way of decision making. It has a potential to present a holistic view on the evaluation of vibrancy, considering the visitors. Thank you for listening to me.
Thank you for such an interesting presentation. I'm going to move to the second presentation, which is the article 200. Let me open it first.
Everyone,
okay.
This is
It's a machine learning approach to translate graph representation into conceptual massing models. So we have the authors here, Kahan Karabagli, Mustafa Kok, Partishwish Basu, Imdad As. Hopefully I pronounce the names properly. I don't think so. Okay, so we're going to start. So you can post your questions on the chat or in the Q&A session. Then we can transfer those questions to the authors. Okay, so let's start.
Kahan Karabagli, the first author of this paper, and joining me today, the second author and my colleague, Mustafa Koç. We will introduce you our research. We would also like to mention the other authors and also our mentors, Partishwish Basu and Imdad As. The name of our paper is A Machine Learning Approach to Translate Graph Representations into Conceptual Massing Models. We believe that machine learning offers significant potentials to provide opposite, timely, and scalable solutions and new ways to study design processes. Our study illustrates a procedure that extends the use of machine learning in the three-dimensional space by generating conceptual massing models, which can be used in the early stages of the design. We use architectural graph representations from previous study As, Pal, and Basu 2018 and explore how it can be translated into various floor plans through HouseScan, which leads to generate a three-dimensional volumetric outcome. The strategy for our study is to introduce a single automated process used within a single software, which will allow to generate 3D conceptual models for the early stage design process. In the later stages of our research, we want to evolve the HouseScan and the floor plan to Blender, which is what we currently use in the study, and to come up with a new fully automated algorithm that could generate a multi-level 3D massing model within just a single process. Currently in this study, we are translating the subgraphs into three-dimensional massing models using existing machine learning softwares developed specifically for the architectural design space. We use HouseScan to transform graphs into floor plans and then process the images to generate 3D massing models by the floor plan to Blender 3D algorithm. In our study, we're challenging the traditional methods for the early stages of conceptual design work to develop a given building program into a floor plan and then into a three-dimensional architectural work. And we're introducing machine learning as the new tool for that. And now my colleague Mustafa Koç will continue.
The graphs used in this project are the floor plan node graphs created with generative adversarial network previously made by us and Basu. The open source HouseScan algorithm was selected and used to convert these graphs back to floor plans. The HouseScan algorithm converts node graphs to floor plans using the generative adversarial network. The graphs in this algorithm belong to one-level plans and cannot form multi-level plans. So we divided the multi-level node graph that is obtained from previous work of us and Basu into multiples and created two separate floor plans using this HouseScan. Later, another open source algorithm that is named floor plan to Blender is used to convert these floor plans to 3D models. Since the floor plan images used by floor plan to Blender algorithm are different from what we have obtained from HouseScan algorithm, the image processing performed by the floor plan to Blender algorithm were performed by us in MATLAB. And the locations of corner points, walls, door details, and shape features were transferred to the text file. The floor plan to Blender algorithm has converted the floor plans into 3D models using the features in these text files and over a server that contains Swagger API. Algorithmically, stacking the 3D models of floor plans is a topic of active research for us. Currently, the stacking process takes place manually using based on architectural knowledge and decision making.
Oh, okay. Alberto, are you there, Alberto?
Yes, I'm here.
Okay, Alberto, you are the next.
Yes,
Yeah,
5.
and you need to, let me stop sharing my screen.
Okay,
You need to stop sharing yours. Okay.
perfect. Yes, I'm
So
doing
remember,
this now.
share the
Yes.
audio in the bottom. Please.
Yes, that is already done. So I'm opening the presentation here. Wait a second.
Okay.
Okay, so here we go. Wait a second. I'm setting up everything now here. Yes. Just there? Yeah.
Yes.
Yes, I think about the wait a second. The share with sound and optimize video clip. Yes. Oh, here we go.
Hi, everyone. We're the Rational Energy Architects here. So AI Inform explores artificial intelligence-informed design flows with a focus on solar designs, where form finding is not simply taken as an optimal resultant shape, but information that informs energy circulation. Such information comprehends beyond a singular unit to the aggregation of units that operate in a straight relationship with an environment and its available energy. So recent material advancements in thin film smart materials that are flexible and lightweight, it offered designers to inspire into new solar design courses that parallel biomimicking generative designs and spurs research that looks deeper into biological systems and their intelligence. So how can designers notate computationally, not just the complexity of the forms in light harvesting organisms, but also their aggregation and distribution, taking solar data as sets of instructions for the design and arrangements of photovoltaic elements in the built environment? Well, artificial intelligence, AI, is a scientific field that studies and attempts to build intelligent entities through virtual agents. These problems are often associated with the automation of intellectual labor, such as that of design. However, they're not necessarily designed by mimicking what humans would do in the same scenario. And for that, we aim to help our AI in learning the ways in which social biological intelligence self-organize. Their development is done around the abilities to artificially reason over complex cases, such as that of aggregating and self-organizing within a solar environment. This research is particularly interested in brew agent-based and machine learning systems, including cellular automata, genetic algorithms, and machine learning pix-to-pix, particularly in how they can integrate and collaborate with one another.
Cellular automata is a physical simulation system that uses an automaton developed by mathematical computational models running a limited set of simple rules. Inside a discrete environment, CA's core elements are individualized and defined as neighborhood, discrete system, abstraction, and dynamism. By activating the discrete grid state on and off, using a seed as an agent, with geometrical outputs as rules of aggregation, CA can produce an enormous set of results. Logic of aggregations can be extrapolated from such systems, focusing on parts and combinations instead of relationships between different seeds in a growing process. This facilitates the testing of alternative data inputs such as solar radiation, iterating possibilities in an evolutionary way. Machine learning algorithms utilize learning strategies to evolve and achieve an objective, and are usually trained by being exposed to a large amount of data or scenarios that they can observe and modify. By learning from data or from craft environments, machine learning carries the biases present in its environment. A poorly constructed dataset can lead to the reinforcement or prejudice, unfit predictions, and behaviors. However, this research chooses to take the advantage of biases in our application of machine learning for the purpose of formulating human-machine interactions.
The intention is to collect data from intuition-based and computationally intensive processes. Designers input with a CA, optimized through a genetic algorithm that takes up 70 gigabytes of data, and use all of that to create the training material that will assist the machine in learning. The objective is to produce a model that learns the hidden patterns of this complex relationship and predicts the results in a relatively instantaneous manner. More specifically, the algorithm should define a three-dimensional shape in a given urban context and the aggregation of architectural components, following a strategy that maximizes the accumulated solar incidences on the surface of a form. Once the ML algorithm has been trained, it is able to predict an optimized aggregation strategy nearly instantaneously when presented with a not seen before set of images. The CA-GA feedback is designed to automate a generative process that takes objective, like location, context, and analysis, and subjective inputs, such as the designer's parametric model. The challenge was the computational cost of three-dimensional data analysis. ML usually compresses high-dimensional data into linear space, and normally such compression results in the loss of integrity of the geometry. Nonetheless, using voxels acting as proxies for complex geometries, it generates not forms, but distribution protocol. Finally, this approach to automate optimization while keeping the complexity of intuition-based biases as part of the generative process can be customized to address other problems. Solar, when the solution is too complex to be directly programmed.
Here are two design outputs from the same pipeline. In both examples, our students face the same problem as initial input, including sharing precisely the same environmental dataset from a coastal community located in Peru. But later, after running the first set of design iterations, both teams finally delivered variations from each node to the next one, creating entirely different results both in shape, density, and architectural program at the end of the whole pipeline. In one case, based more on algae growing optimized shape for solar radiation capture, the other presented a more structural and tree-based shape for the same principle, but mixed with the community football field as a specific programmatic use, generating more rigid design constraints that affected the whole process from human-to-machine design workflow. Participants Tommaso Pilacanchian asked, is it possible to have light harvesting structures that are transparent? A luminescent solar concentrator, LSC, can be fabricated as flexible thin films. Light bounces up and down within the material, transporting solar energy to the edge of a panel to the solar cells, and freeing up the surface for transparency. This gives new opportunities of turning large areas of building in cities as light harvesting surfaces, liberating solar energy systems from being merely on the roof but on building corners and used against reflecting surfaces and even indoors, exploring the modest renewable energy capacities within urban contexts. Thank you.
Thank you so much for your attention. If you would like to get to know more about our work, please scan the QR code, and you may also access our VR gallery, which hosts some of the projects also from students in workshops that we teach. Thank you so much.
Yes.
Okay, thank you, Alberto. We will continue. I'm going to share my screen again to launch the next two presentations. We will continue with paper number 114, Big Data versus Smart Data on the Generation of Floor Plan with Deep Learning. Ricardo Cesar Rodriguez, Marcelo Kenzo Imagawa, sorry, new names for me, Renan Rubio Koga, and Rovenir Bertola Duarte. So I'm going to project the video, but first of all, I need to share my screen. Give me a second. So in between, before doing that, please start thinking preparing your questions. I think we have the opportunity to share because all of you and myself working in the same area. So there is a intriguing, questions about the data model, the data set, the prediction error, and all those kind of things. So start working on your questions to trigger an interesting conversation. Okay, so let me open the next one. Is I say 114. Okay. Okay, almost there. Okay, I'm going to share my screen. Screen 2.
Hello, my name is Ricardo Cesar Rodrigues, and today I'm going to present you the article Big Data versus Smart Data on the Generation of Floor Plans with Deep Learning. Nowadays, we generate and collect more and more data on a daily basis. In parallel to it, deep learning models are also growing proportionally to the amount of available data. This growth raises an important problem of computational intensity. In other words, the more data you have, the longer your training phase will be. Despite the fact artificial intelligence is still in its early days in the architectural field, we can observe a significant growth on the floor plan datasets. But how much data do we actually need to train such models? Does more data always guarantee a good performance? Or can we still have a good performances using less data samples? So the objective of our research is to optimize the relationship between data volume with quality and time of training. To approach the task of generating floor plans with deep learning, we have adopted the image-to-image translation algorithm, which is known as pix-to-pix. However, we can observe that this approach still did not take advantage of massive sets of data, specifically in floor plans. As you can see, most precedents use from 300 to 1200 image samples. Another obstacle to replicate results is the lack of hyperparameters as well as their evaluation methods, which differ from one to another. In our research, we used the R-Plan dataset. This dataset has more than 80,000 images and several layers of information. So we normalized the dataset in 2 domains using equidistance colors in the RGB spectrum. To check if we can train good models with less data and time, first we normalized the dataset, then we divided it into 10 parts. We also divided the whole research into 3 evaluation phases. For each phase, we calculated the Freccia inception distance for each training epoch, which is the training cycle. It's important to use metrics in this type of model because pix-to-pix has a problem of training instability. So it's an efficient way to check what are the best results of the training phase. After each evaluation phase, we also made slight changes in the training hyperparameters to check if the models could get better or if they could be trained faster. It's important to highlight that on the 3 last models, we organized the dataset in a different way. So first, we randomly select 8,000 samples and manually labeled them according to the number of rooms per plan. Then we trained a convolutional neural network with this labeled data to further reorganize the dataset with a different data distribution. This was made to check if a more consistent data distribution would return in a faster convergence. In other words, if the way big datasets are organized will affect the results. These are the results of the first evaluation phase. As you can see, on the red and the yellow lines, both models could achieve a similar result on epoch 110. However, the model of the red line only took 7 hours to be trained, while the model of the yellow line took 55 hours to be trained, which is a significantly faster convergence. The difference between them is the dataset size and image resolution. On the green and blue lines, we can also observe that using a higher image resolution and more images did not make the results to get a better and faster convergence. The same happens when using small image resolutions and less data samples. On the second evaluation phase, we could observe that increasing the dataset up to 20,000 images, we could improve the results even more. However, scaling the dataset to 40 and 72,000 images actually made the results to get even worse, besides taking much longer to be trained. After the second evaluation phase, we noticed that the best training results and hyperparameters were on the fifth model we trained. That is, the model we used 20,000 images with 256 by 256 pixels. So for the last training phase, we reorganized the dataset in a similar amount of data samples, which are 19, 27, and 22,000 images. As we can observe, there is no significant difference between the results of models 8, 9, and 10. Specifically, Model 9 was able to get the results even better in comparison to all the other models that we have previously trained. To analyze why Model 9 had the best results, we projected the image features in space and could see that it's not the data consistency which make the results to get better, but actually the linearity of the distribution. In other words, if the images cluster too much one into another, the model will not learn some features and return less diversity. These are some typical results of Model 9 that achieved the best fit score. This research generated and compared almost 6 million images and took more than 400 hours just for training models. Our results indicate that generating floor plans on the Pix2Pix framework can be difficult when using big sets of data. This means that there is a point where more data samples will not help the model to return better results. Despite the fact that our first model could achieve very good metrics and have a very fast convergence, the results indicate that the best baseline is to train such model using around 20 to 30,000 images, especially due to the way that the metric is calculated. The literature review in concordance to the image quality of the outputs indicate that such model might be applicable to the early stages of the design process. In further research, we intend to evaluate the model using more metrics and develop a digital artifact that incorporates these artificial intelligence models to the early phases of the design process. I'd like to acknowledge the CAPES institution in Brazil for funding this research, as well as the Londrina State University for the opportunity. Thanks everyone for your attention. Any questions, just get in contact.
Thank you for the presentation. Pretty interesting and very dense. Let's move to the next one, and then we will start the Q&A. Remember, prepare your questions, okay? So the next article is 22, if I'm not wrong. Yes, it's article 22. Give me a second. I'm going to stop it.
Welcome to the...
Right, come back to the beginning. This article, let me show my camera again. It's called Daylight and Energy Consumption Assessment of the School Building through Multi-Objective Optimization and Clustering Technique. So today, our authors are Mario Silva, Rafael Garcia, and Joyce Carlo. So let's start.
Presentation of paper 22, Daylight and Energy Consumption Assessment of a School Building through Multi-Objective Optimization and Clustering Technique, written by myself, Mario Silva, and also by Rafael Garcia and Joyce Carlo. Simulation-based optimization, SBO, methods allow combining parametric modeling, simulation, and optimization. Over the last decades, the developments in the computational field allowed software and hardware advances, increasing the use of SBO methods. An SBO methodology has 3 stages. First, pre-processing, which consists of preparing the model for the optimization, defining simulation configurations, choosing the optimization engine, and the optimization algorithm. Stage 2, processing, that encompasses monitoring the optimization process and solving bugs that may occur. Stage 3, post-processing, consisting in analyzing the results. This study focuses on the third stage by applying a clustering technique to optimization results, in order to help understanding its impacts on the building. We create an optimization model based on an actual building that contains labs and classrooms. On the right, we have all parameters used in the optimization process. The parameters are related to building geometry and also with thermal and luminous properties of the construction materials. Here, we have a visual representation of all 10 parameters used on the optimization problem. Parameters 1 to 4 are related to the dimensions of the building. Parameters 5 to 10 are related to openings configuration and size. Based on the actual building and on the parameters presented before, we obtained this building model. For modeling, we use Grasshopper for Rhino. We used Diva and ArcSim to perform the simulations. Diva for annual daylight simulations and ArcSim for thermal and energy simulations. For each simulation, Diva also provides energy use schedules that are linked to ArcSim, so the energy consumption with the lighting systems accounts for savings when the building has good daylight levels. The optimization problem maximizes the used daylight illuminance levels in a range from 100 to 2000 lux, and minimize the energy consumption with all building systems. For the energy consumption, we use the Energy Use Intensity Index, given by the sum of all consumption divided by the consuming area. For the optimization, we use the Octopus and the Hype algorithm with a population size of 70. We define determination of the SBO process based on the visual convergence indicator available on Octopus. The flowchart on the right shows the Grasshopper platform use and the clustering technique application. For the post-processing stage, we apply the clustering technique through RStudio. First, we use the NBClust package, which provides different metrics to determine the ideal number of clusters based on the database provided. Then, we use the k-means method to divide the solutions into groups. After defining the groups, we analyze their formation by relating parameters and fitness functions values. The SBO process resulted in 3,448 solutions with unique values for energy consumption and daylight. Initially, we intend to apply the clustering method only to the Pareto solutions, since they represent the best outcomes for an optimization process. However, the Pareto front only had 12 solutions. Then, we decide to apply the clustering technique to the whole data. On the left, we have the frequency of votes for the 26 metrics in the NBClust package. And on the right, we have the division of the solutions according to the ideal number of clusters. Group 1 in green has solutions with best performance for consumption and worst for daylight. Group 3 in orange has the best performance for daylight and the worst for consumption. Group 2 contains the Pareto front and presents solutions with good performance for both fitness functions. Based on the clusters, parameters x2 and x4 related to building depth, x5 related to openings height, and x7 related to shading devices opening angle, have the most significant impact on determining the clusterization, since they have different distributions on each cluster, especially on Group 2 with the best solutions. The results also pointed out that low values for building depth and higher windows provide the best solutions with low energy consumption and high daylight levels. The results also show that X7 presents the highest correlation with daylight levels, since it has a similar distribution for groups 2 and 3 that contain solutions with the best luminous performance. Concluding, the use of SBO methods can enhance buildings' performance for daylight and energy consumption. The clustering technique allowed to analyze SBO solutions by relating parameters and fitness function values. The results also show that geometric parameters have the most significant impact on the best solutions. The study also provided a new approach to analyze SBO solutions that can be replicated in other SBO studies. We would like to thank CAPS for funding this study and all of you that watched this presentation.
Okay. Thank you for the presentation. I'm going to stop sharing my screen. Thank you. I mean, we have seen quite a diverse catalog of topics. So let me read the titles again of the presentation. The first presentation was data-driven participatory decision model proposal in the context of urban vibrancy. The second one, a machine learning approach to translate GANs-generated graph representations into conceptual massing models. Third one, AI-informed intelligence and aggregation for solar design in the built environment. The fourth one, big data versus smart data on the generation of floor plan with deep learning. And the last one, daylight and energy consumption assessment of a school building through a multi-objective optimization and clustering technique, sorry. I mean, what we have here is a wide catalog of approaches to take advantage of existing technology. Is yesterday in our conversation with the keynote, Greg Lin, at the very end, we were, asking about his thoughts about the notion of early adopters. I mean, obviously, everybody here is an early adopter of those techniques that are under development. We know there's a lot of challenges and it's very promising. And I would like to invite you to discuss about the challenge, because I have a long list here, right? This is an open question, then we can dive into the particular topics of each one. But if I can put a list together, for example, first article, I have questions about the data validation, the data we use, right? The data we survey from reality or from data sets. I mean, what is the validity of that data? Can we trust in that data? How clean is that data? Is complete that data, right? There is an issue or a big question, not an issue, I mean, a big challenge and question regarding the validation of the input data, right? Another challenge, I mean, I see is one other question is the error, the percentage of error in the prediction, right? Or do we have enough input parameters to describe the phenomenon we are talking about, right? Computational intensity, right? There is this paradox. In order to predict in a matter of seconds, I need to invest 400 hours to do that, right? There is a very interesting paradox there. So if you have so much information, maybe, you don't need to do that, right? Data volume, right? Time of training, right? Post-processing the results. So making sense of the data. We have seen this technique of clustering in the last presentation, trying to make sense of the data. In my experience, what we do is we use another technique that is in the same direction, is sensitivity analysis, which is looking for the same thing. What is the correlation between inputs and output? There is any correlation, right? If there is any, what is the reason? I don't know. I mean, there is a wide catalog of challenges. So I would like to hear from the authors. What are your thoughts about this? I mean, what are the challenge you're facing, and how do you see the next steps, right? You can raise your hand and start. Okay, Dulce, are you going to start, right?
Yes, okay. In terms of the validation of the input data, and I mean the collection of the big volume of data about the places, actually, it was challenging for me to cope with this amount of the data, because since they are user driven, it takes so much time to standardize the data according to making them in a data set. And then I actually validate the data sets with the real data, the administrative map results. And that's why I compare them about the place information. So, and actually the Google Places API results mainly was validated. I mean, that was correct with the same place in the map, because I observe it in my site observations when I visited there as well. And I also double check it, some of them maybe through the Google Maps result, the maps result, not the API results, but some of them are wrongly checked, and I have to eliminate them. So yes, that it takes lots of process for me, but lots of I mean that was time and labor intensity work to do. And you are right, maybe I have to do a sensitivity analysis as well. This was my first experiments with data, and how can I actually process data, how can I inform how can I generate information using that data. But the sensitivity analysis and actually the validation of the data was also important concerns that I will take into consideration. And you mean the percentages of the error, but if these percentages coming from the surveys, actually the number of the participants was so limited. So I both increased my sampling sizes, I mean the analysis of the units from neighborhood to the grid scale to increase the sampling. And I also increased this participant number. This was the first initial results of the survey. That's why I mean the percentage of error was bigger than I thought. I think that if I increase both the sampling size, and that will increase the prediction capability of the learning algorithm as well, since the sampling size getting bigger. And if I ask more respondents, more participants, this survey, the evaluation results will be changed accordingly in parallel. And I think the error percentage will decrease more, I suppose. But thank you for these. For your critics.
May I speak?
Yeah, sure, please.
I think what Goose is saying, like her challenge is like to get participants to evaluate something. Like we have to trust nowadays on the available data we have, and sometimes we need some type of data that is not available. For example, in her case, she needed participants to evaluate and decrease the error rate. In my case, I think it's more about a process that was not tried at this scale before, but I think it returns guidelines for how should we train models like this. You know, we don't need to set up like for this specific algorithm, right? Because if we get other algorithms like graph neural networks or natural language processing, we're going to have other types of performances, and the algorithm works in a different way. So it's specifically for pix-to-pix. If we're going to build a data set, for example, of Brazilian houses, of houses from a specific city, we can already explore this type of technology without getting too much resources. So I think it's the opposite from her case. We're trying to make the training faster, and in her case, for her predictions to get better, she needs more participants. All right, so there's like a contrast between one another.
That's right. Anybody?
Hi.
Hi.
Maybe also thank you, Gilles and Ricardo, for an insight to the challenge. I think one of the challenge that probably goes through all the project is how one algorithm bridges another one. So like the translation between data, which is also exactly what our team is facing, because we're going from Houdini, Grasshopper to a custom Python framework in Visual Studio. And then some algorithms, they understand 2D data, some algorithms they understand array and stuff like that, but they're all artificial intelligence. So how do we actually make the data not just as an image, but also as sets of instruction that can help different algorithms to learn between one another? And I'm actually really happy to see that the first paper go from HouseScan to Blender. So it's like between open source. And also at the same time, the challenge of how do you actually translate between 2D and 3D as opposed to just a stacking mechanism. Like, can we have line tracing point or teaching like a pigment neural network to actually, trace itself around a floor plan and thus be able to understand other aspects of the impact of what we're generating? I think that should also be an interesting discussion.
Yes, another thing that maybe is really relevant is related with the lack of three-dimensionality that we are facing with this techniques. As we are just starting to understand the real challenges in this in all these ideas that we are running now. Well, architecture is based on the space, three-dimensional space, and till now we are just trying to understand how to translate this to the information. For instance, pix-to-pix, the things that we are working with in our case, how to use pix-to-pix as a translation tool from 3D from 3D to 2D and then to 3D again. So it's something super challenging that in a way maybe in the near future we are going to develop to be developing a proper 3D-dimensional machine learning system instead of these hybridizations that we are doing now. That's something that as early adopters we are facing all these issues, but it's really interesting because we are pushing in time by time the boundaries of what we are doing.
Yeah, that's right. I mean, sometimes we develop something. I mean, I'm working on. So let me reintroduce myself. I'm Marcelo Bernal. I'm the vice president of SIGraDi, but I'm also the director of the design process lab at Perkins & Will. And we in the professional practice, we don't have room for too much percentage of error. We need to be very effective. So the kind of things we're doing are more in the problems we already know. We have a well-described set of problems. For example, energy is the easiest, most difficult thing you can do. Why? Because there is tons of parameters, but we know all of them. We have been working as a community in that problem for 25 years. So the level of prediction we have there is very precise, it's acceptable. But however, in others, even something like daylight, in daylight we are having issues because you have the typical window to wall ratio. Some of you are working in that area, but then in order to define the actual shape of the window, to the right, to the left, up, down, the center is a longer one, it's a vertical one. You need more descriptors, more parameters. So then you're increasing the number of parameters and you get into this crazy paradox. It's so large, right? Because you need so much description to increase the prediction that in some point you need to stop. So we, in early design stages, we're accepting sometimes 10% of error, even 15, right? Which is, in a statistic, is totally unacceptable. But for us, it's good to go. Why? Because there is a balance, right? In others, 2%, 5%, which is good, right? In a matter of seconds with a small sample. But in others, it's crazy. I was in a conference like 2 years ago, Advancing Computational Design, a professional conference, very interesting, and some researchers from a Japanese company, I don't remember the name right now, they were working on CFD, using machine learning to predict CFD. CFD, computer fluid dynamics, takes a while for one iteration, a couple of hours, maybe a day, right, to converge. So using machine learning to accelerate, to speed up that process is sounds very promising, right? Yeah, the reported error was around 30%, which means totally useless, right? Totally useless as a prediction. But that was 2 years ago. I would like to know where those guys are, right? I see this army of people exploring, right? Trying to understand every problem, because we need to understand the specific problem itself, right? CFD is one type of problem, right? Dealing with people, another problem. Energy, another problem. So, and each problem and each algorithm is a kind of two-dimensional metric that is very interesting to explore, right? So those are my thoughts. I mean, at least my personal experience is pretty challenging. So I would like to ask you, unless you have another comment, to move towards the education, because I know some of you are educators. What have been your experience in that area, teaching, sharing with the new generation of designers and these kind of techniques? Good. You can come back to the previous question if you want.
Well, maybe we can talk a little bit from the bottom of what is happening here already with the machine learning and all these implementations, including as well how we are linking now this with well, using some other tools like evolutionary solvers, as well with Fusion 360 and Brian Man with Autodesk Clouds, etc. And as for what in one hand, and the other hand, we are working with more the classical way, let's say, with coding and all these other things. And in a way, this is something super challenging, because year by year we are reevaluating what we are doing in terms of, just in case, when the last year we are starting with this idea of okay, let's try to mix to introduce these generative solvers with as an open class. Let's see if this works, and then it's working. So let's try to introduce something new now. But then it's something that we were talking yesterday about that in one of the masters in which I'm teaching with the engineering and architectural design. Well, this is the chance that we have to test few things, and then let's evaluate what is happening with these things. So it's in the academia, in which we can in a way we can find this degree of freedom for us researchers, as educators, as you said, because in the professional practice, it's slightly impossible to have these opportunities. So, and as well, the students are really responsive about these new things that are coming year by year, and in a way, we are kind of we are working together with the students. So it's not about just us working in complete independent way. We are being really we are working as a team with the guys at the same time. So every year we are really impressed about the results that are coming, because every year is something that is something that is let's say funded by the previous year. So it's something that is growing and growing and growing. And maybe, as you said as well, maybe this idea of working with artificial intelligence and all these machine learning processes is going to be then maybe something so as business as usual. Now it's something quite new, but 5 years ago was something completely, let's say, something unique. Now all of us we are working in a way with this, but then it's going to be good. Something, I mean, let's say, part of the industry, something standard.
Yeah. Any other comments in that matter? You can raise your hand. I think I have some question in the chat. No, it's not a question.
I would like
okay,
to...
Daniel. Okay.
Hello, Marcel. How are you?
Hola.
Everything fine?
Everything fine. I've seen you in many presentations. You're
Yes.
always in the.
Yeah.
You're
Thank you,
been
Daniel.
very active.
Yes.
Yep. Trying to look for a lot of things. I would like to ask to all the participants if they think that machine learning in the result that you are achieving, that it's possible to achieve some consensus in some kind of parameters and some kind of procedures in order to establish standard methods to achieve some predictions, some valid predictions. Let's say, do you think that according to your experience that is possible to converge to a kind of standard method or standard methods in order to achieve in an efficient manner the the best results that is after all the purpose or the goal of machine learning process is trying to achieve better results in the performance of the process. So do you think that it's possible to according to your experiences to achieve a standard method, standard parameters for some kind of problems that are going to facilitate to turn more easy our future tasks utilizing the machine learning approach? It is a generic question. I'm not specifying to some panelists in concrete, but it is an open question.
May I answer?
Yeah, please.
I think it's a difficult question to answer because it depends on what kind of algorithm we're using and how much parameters we have. So, for example, in machine learning, we have some problems like underfitting and overfitting, and like underfitting is when you show only few data samples and the machine is not able to understand. Or overfittings when you train so hard and you have so much data that the machine cannot generalize a type of information to make a certain prediction. And we have another phenomenon called the curse of dimensionality. That's like when the dimensions of the data points are so high dimensional that it cannot be synthesized into one prediction, right? Or there's not a single final solution. And I think it depends on the challenge we are approaching. If it's like we're trying to predict the solar performance, or if we're trying to predict the spatial organization of a floor plan, if we're trying to predict, I don't know, the workflow in a city, I think the answer depends on the amount of parameters we have. I think that's it.
Just to jump in, I think a more personal comment is that we should thank this guy that there are no standard way, or else everything would have been automated by machines by now. And because it's non-standard architecture, that's why creativity is still relevant. Architects are still relevant. And I don't think in a short amount of time, machines will be taking over our jobs, as many people are afraid. And I think that goes back to the education question. I don't think it's so much about just educating humans. It's more, I think all of our works are actually a collective work in collectively teaching machine, which we can all see that it's very single task. It's kind of dumb. And that moves us to the idea of distributed learning networks. Like if the next global challenge is perhaps, is there a way that we can all continuously be training neural networks all together, which right now with supervised learning is super difficult because we have to delete the data point and retrain the entire model. So it's almost like a vision where there should be a way to continuously mine real-time data onto a common database where it will be fitting the machine. And then maybe also BIM with Newtonian physics can evaluate what the neural network has output and real-time fit it back to it, which our workshop this time at SIGraDi was trying to attempt at breaching that. So Victor?
Yeah, anybody else want to comment on that? I can share my experiences. We develop in-house a system for energy analysis, and for 2 years we were working on the data model. What are the inputs? What are the assumptions? So basically, you input geographic location, some general description of the building, and the system makes a lot of assumptions based on code, right? And we have that standard set of data, and that is helping us to speed up that process. But there is no machine learning that works in the cloud, right? It runs pretty fast and runs everything. It's like a gun machine, right? Very brutal, right? Just computational muscle. But now we are combining that, trying to use that to generate the data set really fast in order to use some of the different algorithms that are out there to do that. But that problem is a well-described problem. You can standardize that problem, but still it's a schema you can extend. So for me, answering or addressing the question about standardization is I believe in data models that can be potentially standardized, but extensible as well, Daniel. I mean, I believe they should be flexible enough to accommodate the complexity of the architecture, because not every, for some reason, people like to buy the same car. They don't have a problem, but everybody wants that unique building, right? But I think we need to work probably in the extensibility of those models, but we don't have the models yet. I mean, and different areas is totally different what you the type of the model you need to use. And some of you were commenting that depending on the problem is the algorithm you use. We have been using some of them for just to validation of the size of our data sample. So if the algorithm is telling us with this small data sample, I can predict with an error of 5%. Okay, we don't run the machine learning. We use the small sample and we do sensitivity, and we make decisions based on a small sample. And we only use the other one. I mean, it's good enough for prediction. Okay, we are good to go. We can make assumptions. Why? Because there is a general thing, at least from the profession, which is response time. You need to be fast. Design teams will make decisions with or without you for some other reasons. So then we need to be fast, right? And this area seems to be very promising. And the standardization can help, but it depends on the problem. And in some of them, we are in baby steps, I believe, right? Anything you want to ask to the other authors about their specific work?
Can I make a provocation?
Yeah, please.
Yay, super. So thank you very much for the presentation of the papers. It was really interesting for me to watch them all, especially because what used to be a very niche or rocket science research 3 or 4 years ago is becoming very popular, and you can see people researching this topic from right now. We have south of Brazil to China to Chile to everywhere. So now that we are putting our hands on machine learning, automation, on genetic algorithms, and we are becoming very skilled on it, I think that the interesting question to ask is, what are our political and economical goals behind that? Is it only increase of productivity, or is it really producing a qualitative change in the built environment, or also in the quality of life of the designer, the architect, or the builder? So this is my provocation for you guys. Thank you very much.
Thank you. I think Alberto, you have your.
Yes.
Right?
Yes. Well, in terms of provocations as well, I was just remembering that here we were talking in one of the seminars here in the Bartlett about these two ways that machine learning is it's a way. Machine learning is built in two different ways. One way is related with data. Like here, we have several nice examples and research looking into how to work with the data in a quite serious way. But on the other side, we have the machine learning in a more being explored in a more aesthetic way. Let's say, well, playing with images, trying to create more perceptual emotions and other things. And I'm not really sure of this. In a certain point in the future development, we are going to merge these two ways in one again, because it's something super. Can be something super interesting. I'm not sure what you are thinking about that, because in our case we are working completely out of the aesthetics sometimes, but then later we must to return to that, because we need to create proposals with this in a provocative way. So it's something super challenging that I'm not sure what if you are facing something similar with your experiences.
Anybody?
Well, I can add something to the question of Victor. Maybe the ultimate goal of this, maybe the hope, I believe, like in the architecture, in the design process, there's a lot of parameters we know now, and until now, you have to try the design. You cannot experiment on it. Like, you build the building and it is there for 50 years, 100 years, or even longer. So you cannot try that. If it is mistaken, you have a huge mistake there. But with machine learning, the capacity of processing capacity of the machine learning, you can process these a lot parameters, a lot data, like in a day, or like in hours. So it can maybe create the ultimate design tool. Maybe it cannot design, but I think personally a machine can design with learning enough data. But let's say it can be a very good designing tool for designers.
Yeah, definitely it can be. I will address Victor provocation as well, but it's not me. I mean, it's basically transferring the experience from the pre-opening of the conference on Monday. We start early that Monday with a female panel called Experimental Media and Activism. Marcela Godoy was the moderator with 4 guests. And one of them, it was a very interesting one, but one of them, an artist, Eunsu Kang, was doing this thing. She was getting picture of people, right? And feeding the algorithm in order to predict what a person is, right? In a sort of very artistic way. And created some blur images. Some people were asked, I mean, in the survey to answer, is a male or is female? She was questioning the notion of classification, gender, and all of that. And there is two. And for example, one of the answers was people were saying, no, it looks like David Bowie or something like that. Like two people answered that. Others answered like 60% female, 30-something% male, and categories in between, including David Bowie. But what was interesting from her analysis of this, when she was presenting another example, first, there is a lot of cultural, let's say, drivers that are influencing our interpretation of the data. Okay? That was the first top point. The second point was also even further. She was predicting or classifying Asian girls, right? And when she went through the database to face recognition in airports and all of that, she realized that 70-something% of the Asian girls were smiling, right? And then she built an interpretation about what is the reason of that. And she was looking into cultural patterns, right? And the cultural patterns basically are telling in that society that girls need to smile, right? And maybe if you go to my country, you will have the macho, picture, right, in the database, right? Because it's another bias. So then, what she was looking for through the data wasn't the prediction of the performance indicators. She was looking for stereotypes, for biases. That was the things she was looking for. It was, for me, it was shocking because I've been trying to describe my beloved window. I mean, what is the right parameter for my window? What is the right parameter to describe this phenomenon? But she was looking something else in that data. She was looking for those stereotypes, and I think she's addressing your question, Victor. I mean, pretty nicely. For me, it was like a revelation, that panel. So you have the chance, take a look. It's very interesting, her work from the artistic perspective. I mean, giving a completely different angle of what we're doing.
I don't think there are too much time, but maybe just adding on to what Marcelo was saying, which I think was pretty on point. I guess at this era, we are all trying to find a frontal line to fight. Like there are so many battles, like each of us identify ourselves with one. If we don't, it's almost like we're, just irrelevant. But I guess that also, for instance, my fight with like going back to what actually characterize an intelligence. And according to Wiener and Schrodinger and all those guys, they would be saying like, information entropy increased globally, but decreases locally. But what does it mean? And I think looking at all of the work today, it inspired me that, if we're using machine learning to generate a lot of options at an almost instantaneous manner, then it's increasing information entropy globally. But then for designers to actually rationalize the decision and implement it, then our intelligence is to decrease entropy locally. So together we almost collaborate to calibrate the system, which I think it can fakely tie to a democratic digital practice in a sense that not so much as who get to do what, which is what we're fighting mostly, but what options are actually there for people to choose, which right now they're not so much, I don't know, like feminism, climate change, all this battle line are still quite limited.
Yeah, but remember, potentially there is some bias in and stereotypes in that data.
Right? Which is why overall we need to conduct that wisdom and responsibility when we do these works. So the wise ways of using technology is the overall that we need to all never forget.
Yeah.
I also want to add something to the Victor's questions. From my studies perspective, I would like to include the user dynamics when we are evaluating and while we are making decisions in terms of the urban planning, because generally this kind of planning decision was based on the building characteristics, physical attributes, and so on. And then we observe how that's gonna reflect to the user behavior or user density. So even though the challenges that the data provides us or other challenges derived from the machine learning and other artificial intelligence methods, I think benefiting this diversity of the data and including them into the decision-making process was beneficial to, for instance, in terms of the urban scale for getting an inclusive decision and for considering other layers that we generally didn't take consideration. In a way, we start to monitor and measure the user dynamics, and it makes them the ephemeral layer of the users that becomes visible. So it's also creates a potential for us for more inclusive decision making. Maybe that would be a benefit for these kind of technologies.
Yeah, a greater purpose. Okay, any final comments? I think we are kind of in the time. Then we have a few minutes for break to start the new session. Any final comments? Okay, if not, what about turning on your cameras and we can have a selfie? Right? Who has the camera there and wants to participate? Okay, ready? Smile. Okay. Yeah, we are capturing. I mean, we have a small group. More people is turning on the cameras. Okay, good. It means they are listening. Okay, great. Smile. Okay, you will see that soon. And thank you, guys. It was a great session. Okay, keep doing what you're doing, right? Keep and find the battle to fight for. Okay. So we have a few more sessions, and then we will have the closing ceremony. We have new bylaws. We have been updating what our practice, because we originally had some, I mean, bylaws in like from the late 90s. We never updated them. And gradually we were changing our practice, and suddenly we realized we were kind of far apart from that. So we did a major update in order to, update and also evolve and project the organization. So the voting will be during the closing ceremony, and we need your support to validate or not that work. Okay. Thank you. Bye.
Bye. Thank you very much.
Bye-bye.
Bye.
Thank you, guys.
Bye. See you guys.
Yeah.
Let's
And
be
talk
in
to
touch.
each other. Share emails. Bye.
Yes. Bye-bye.
Bye.
Hi, Simon.
Hello.
Hi. Sorry.
Yeah, what about the voice?
Hi, Sema.
Hello.
Now I can listen too. Sorry.
Great. I have a question beforehand. I think we are already in